Today we've got Dr. Giacomo Cordoni.
Perfect.
Yeah. Did not just Google that. And we're talking about something interesting for once, which is stars. So I'll let you go.
Okay, so first of all, thanks for having me here. I'm very happy to present my work and give you, so for this talk, since I had 40 minutes, I decided to, instead of just talking about the recent developments of the field, I decided to make more of a, like an historic overview of how do we start young star clusters and what do we know. And I hope to convince you that we don't know them that well, or at least not as well as we think we know them. So just a few words about myself. So I did my PhD in Italy, in Padova, and I just recently joined the Australian National University as a postdoctoral fellow. And my main research topic are the one that you see on the right that are borrowed from Indiana University because they look very cool. Basically everything related to like stellar population, star clusters, stellar dynamics, and in the context of the galaxy formation. So if you are interested in any of those topics, I would love to have a chat. But today I will talk mostly about star clusters. So we will go from young galactic and extragalactic like open clusters to ancient massive globular clusters in the Milky Way. So historically, they have been very important because in the Milky Way, we can divide clusters in two main classes. So we have old globular clusters that if you want to describe them within a few words, basically they are very old, massive, compact objects that live mostly in the galactic halo. And at the opposite end of the spectrum, we have young star clusters, and particularly in the galaxy, we have open clusters. So they are very loose, very sparse groups of stars, and they can host like tens of stars to around 1,000 of stars. So they're very like less massive with respect to globular cluster and less compact, and they mostly, so this is better, mostly live in the galactic disk. So studying star clusters, both old globular clusters and young star clusters, can provide very important constraint in the context of the formation and evolution of the Milky Way. Because on the one hand, we have old globular clusters. They're around 13 gigayears old, so they provide a window into the earliest phases of the Milky Way. On the opposite end, we have young star clusters that are like a few tens of megayear old to a few gigayear old, so we can use them to know what happens next. So how star clusters form, how they populate the Milky Way, and so on. And in the context of stellar astrophysics, they're even more important because we can use color magnitude diagrams to study star clusters and to understand how stars form and evolve. And in particular, if you look at the CMD here, basically it's the observational counterpart of the HR diagram. We can basically identify all the different evolutionary phases of stars. So we have like main sequence stars, to North stars, to giant branch, and then evolved stars. So I couldn't highlight those phases individually because they're a bit overlapping, but we have RGB stars, AGB stars, and H branch, horizontal branch, or red cloud stars, depending on the cluster. And so these are very important because we can use them basically as benchmark to understand how well do we understand star formation and star evolution. And this is to quote from a not so recent review, star clusters were recognized as excellent laboratories to study theories of stellar evolution because basically they were a simple stellar population. So they were formed by stars that were coeval, co-spatial, and with the same metallicities and overall chemical properties. And so why is that? Why did we believe that? The reason is that if we look again at the globular clusters like here, we can use different instruments to get very good photometric observation. This is with HST because it's the globular clusters. And if we look at the CMD, what we can do, we can compare that with theoretical models. So specifically with stellar isochrones that give you basically a snapshot of how a stellar population looks like at a specific age. And yeah, you can sort of see the blue line is what we think, the prediction that we have from the isochrone of a simple stellar population, and you can see there is a very good agreement between the observed CMDs and the theoretical isochrone. So the conclusion is that, okay, Globular clusters are composed of simple stellar populations, so stars form all together at the same time from the same molecular cloud in the same star formation episode, so they have the same properties. And so this is where we start. So I put 1987 because that's where we started to realize that something was a bit different. But okay, why is it different? So this CMD is made in the optical filter, so HST optical filter. And so far, okay, all good. So it's actually very similar to a simple star population. However, HST also have ultraviolet filters. And when we look in the ultraviolet regime, we start to see that something is like completely off. And in particular, you can see that in that CMD, there are multiple sequences on the RGB, on the main sequence. And so this is completely different from the prediction of the simple stellar population model. So today, we know that globular cluster has multiple stellar population. In particular, each of these sequences that you see in the CMD is a different stellar population with a different chemical pattern, let's say, in particular in light element abundance. So the multi-population phenomenon is very interesting because it basically has reshaped our understanding of globular clusters, suggesting the stars within a single cluster can form through multiple star formation events, so we can have multiple stellar generation. This is very important because this is telling us how these clusters can form and how star formation can take place. Don't have the time to go through all these fields. This is a completely research field, but I'm very interested in that. So if you want to have a chat about that as well, about globular cluster, multiple star formation, multiple population, happy to do that. So please come and talk to me. And so, okay, this is where we are. In the early 2000s, let's say, we realized that globular clusters are much more complex. We have multiple star formation episodes. The punchline is that after almost more than 20 years, we still don't know how this population formed. So we have some idea, we have competing scenarios, but there is still no agreement. So we don't know how this population formed. And one particularly difficult point is that we are trying to understand how this population formed 13 gigayears after they formed. So it's very difficult because it's like try to understand how dinosaurs lived only based on their fossils. We can do that, but it's not super straightforward. What would be very good would be to study multi-population while they form. So to keep the metaphor living, we want to study a living dinosaur so that we can see how multi-population form, or at least study them just after they form. So what we want a young massive globular cluster. Do we have some of these? But unfortunately, not in the Milky Way. We don't have such massive and compact clusters. We only have open clusters, but they are younger, they are not as massive, not as compact. But we have some examples in the Magellanic Clouds. So they're not far away from us. And the question is, can we actually get very good photometry for star clusters in the Magellanic Clouds? And luckily for us, the answer is yes, thanks to moving. Thanks again to HST, we can actually resolve each individual star in Magellanic Clouds cluster. And what it means is that we can actually build the color magnitude diagram in the same way that we do for globular cluster in the Milky Way. So we can actually compare the CMDs of young star cluster in the Magellanic Clouds with what we know about globular clusters. And this is a CMD of a 2 gigayear-old clusters. You can see that we still see the main sequence. Okay, no cursor, sorry. You can see the main sequence, you can see the turn-off. And if we zoom in a bit on the turn-off, and if you squeeze your eyes a little bit more, you probably see that the turn-off is not very narrow. So it seems to be that there seems to be like two sequences in the turn-off, and there is a bright one and a faint one. And so we were very happy about it when we realized this, because the straightforward conclusion is that, okay, we are actually seeing that the turn-off is extended, so it's not consistent with, again, a simple stellar population. And even more importantly, we are looking at multiple stellar population in Magellanic Clouds clusters. And again, this is very important because this means that we can study multi-population just a few gigayears after they form. So not 13 gigayears like in globular clusters, but much more soon, let's say. And so in 27, more or less, we realized that multi-population were a feature of Magellanic Clouds clusters. And even more importantly, if we compare that with, again, stellar isochrons, so with theoretical models, we can see that we can reproduce the turnoff with two isochrons with different age. So we actually are seeing multiple, or maybe seeing multiple stellar generations. So we are actually witnessing the formation of multiple stellar populations. So we have our living dinosaur, we can study that, and first, maybe we can understand how multiple populations are formed. This is 2008. So and thanks to, again, HST, we could get more and more data. So not only one cluster, but we could extend the study to multiple star clusters in the Magellanic Clouds, even younger globular clusters, younger Magellanic Clouds clusters. And you see that on the right side, you have one of the cluster which I showed before, again, the sort of bimodal turnoff. But in the younger cluster, we can see that we have also a split main sequence. So here you can see that main sequence is sort of double, and you can sort of follow these two specific sequence. So good. What this is telling us is that Magellanic Clouds cluster has multiple stellar population, similarly to what we see in globular clusters. All nice, but if you want to play at the devil's advocate, you may ask, okay, is that the only explanation that we have? Can we explain these features, so the split main sequence and the extended main sequence turnoff with other physical mechanism besides age difference? And luckily or unluckily, depending on the point of view, the answer is yes. And specifically, stellar rotation actually plays a very important role because it affects let's say, what we see in a star cluster. Specifically, it affects the photometry of very young star clusters. And so the basic idea is that if we have fast rotating stars, basically they would result that they're like a fast rotating stars will have lower luminosities and lower effective temperature. So in the CMD, these are theoretical models. You can see that red lines are fast rotating stars. They are a bit on the right, so they are cooler than fast rotating stars. A bit different in the situation in the turnoff, but between the quote and the models, there are like 15 years difference. So now we know a little bit better what is going on. And so rotation plays a very important role, but not only rotation, because we are actually observing this star. So another important effect is the inclination. So the inclination between the line of sight, so us, and the rotation axis of these stars. So if we look at the star pole on, so in darker colors, we will have something that is hotter and a little bit brighter. While if we see something like edge on, so the star rotating like this, then we get something a bit hotter, sorry, a bit cooler and a bit fainter. So if we combine these two effects together, what we have is that stellar rotation can spread stars in the turnoff. And in particular, you see that here we have the extended main sequence turnoff that we saw in the clusters. And if we combine rotating and non-rotating stars, we also have this split in the main sequence. So actually, rotation in principle can explain very well what is happening in Magellanic Clouds clusters. And so in 2009, we have this dichotomy between like age differences and stellar rotation. And the main problem is that in the turnoff region, these two effects are almost degenerate in the sense they can both produce a split and they can both produce a spread in the turnoff. So the question is, how can we understand which is the right one? And this is not so easy, but what we can do is try and look at the cluster and test the predictions or the results with different assumptions. So let's start, for instance, with the age differences. We can say, okay, let's assume that all the spread in the turnoff is given by age differences. So like each star here has a different age. And what we can do, we can use theoretical isochrons to go from this here, so like a distribution in the turnoff, to an age distribution. And by doing that, we can understand what's the age difference that we see in these clusters. And if we do that for, it was a zoom in. If we do that for a lot of clusters, we can compare the, let's say, the age spread that we measure with the cluster age and see if there is any trend which may tell us something about how these stars are forming. And when we do that, we see that there is a very good trend between cluster age on the x-axis and the age spread in the y-axis. And at first, this looked very peculiar because here you would have to assume that older clusters have a longer star formation history, or like multiple star formation episodes spread apart, while in younger clusters we have shorter star formation history. And in the context of star formation, this is not so straightforward to explain. So is there something more? Can actually stellar rotation explain this pattern? To answer this question, what we can do, we can like simulate clusters with fast rotating stars. We have that spread again, and then we remeasure the age spread in this case. So like we simulate the population, we see the spread that we know is given only by rotation, and we say, okay, let's interpret that as an age spread and remeasure the age spread in the turnoff. And what we see is that the prediction from the stellar rotation models are actually in very good agreement with Magellanic Cloud, with the age spread that we see in Magellanic Cloud clusters. And there are less points here because I couldn't find the same figure. It's probably lost in my old notebook, but it's somewhere there, but I could only find that, and it still gives a very good idea. So in 2015, we basically knew that rotation played like a major role in the shaping of Magellanic Cloud clusters, and we sort of assumed that we had to, let's say, input a bimodal rotation rates to explain the split main sequence and fast rotation rate to explain the spread in the turnoff. So, okay, age difference is not the right model, stellar rotation is actually the answer. However, the agreement is good, but it's still not perfect in the sense that there is still like some sort of residuals here, there is a large scatter here, and more importantly, if we want to reproduce exactly the CMD here, I don't know, maybe you can see there are two like very light blue lines, so we still have to assume that there's a residual age spread to match the bluer part of the turnoff. So, okay, rotation is there, but it's not enough to actually explain what we are observing. So in 2017, there was this debate whether we had to include a residual age spread, not of a few hundred mega years, but maybe of 50 or 100 mega years to explain this, to reproduce the CMDs of young star clusters. But we also had groups that claimed that they could actually explain everything just by assuming that stars actually spin down during their evolution, like by tidal locking or some other effects. And if you have a star that spins down, basically it looks younger because it has like a enhanced mixing due to stellar rotation, and so it looks a bit younger. And so we couldn't understand what was the right one. So in 2017, we basically made a step back and we said, okay, it's not only stellar rotation is there, but it's not the only thing. We need to also include a residual age spread. And then came 2018. Actually, I think it was between 2017 and 2018. And the second release of the Gaia mission sort of revolutionized the field of star clustering, particularly in the Milky Way. And so we had much more data, we had better data, we had astrometric photometry, very good astrometry, very good photometry, which allowed us to study basically open cluster as well, which at this point were basically not considered. So we were studying globular clusters, we were studying Magellanic Cloud clusters, but not open clusters. Thanks to the Gaia data release, what we discovered is that, okay, the extended main sequence turnoff is not a feature of Magellanic Cloud cluster alone, but it's also a common feature in young galactic open clusters. And this may seem like a straightforward thing, but it's not, because open clusters are much less massive than Magellanic Cloud clusters. So what this is telling us is that maybe it's not an environmental effect, but it's just an evolutionary effect. So all star clusters like undergo the same step, like the same evolution path, and then the extended main sequence turnoff is a consequence of this. And what we see here is the same plot, the comparison between the same plot for open clusters on the left, Magellanic Cloud cluster on the right. You see that, again, we have a very good agreement with the prediction of stellar rotation. And in 2018, we also directly measured rotation rates, stellar rotation, in both open cluster and Magellanic Cloud clusters. And you see that we have sort of the same trend. So here is stellar rotation, here is stellar rotation, here is the magnitude, and you see that we have these blue stars that are slow rotators, here a bit less, but still is there, and the slow rotators are mostly populating the blue sequence in the CMD. So what is the conclusion of this? the conclusion is that, first of all, stellar rotation is like the main driver again, so go back to stellar rotation being the main driver, and that Magellanic Clouds clusters and open clusters sort of behave in a very similar way. So they both have extended main sequence turn-off, which can be explained by stellar rotation. Okay, this is very nice, but we still haven't answered our question. So, is there a residual age spread? This is what we want to know, because we want to understand if multiple star formation episodes are actually taking place, or they can happen, or if not. And again, the turn-off is highly degenerate between stellar rotation and age differences. So how can we break the degeneracy? How can we find a new perspective? So in 2019, it's now, yes, 2019, we came up with a new approach. So not exploiting the main sequence turn-off, but exploiting the main sequence turn-on, which is not very known, it's not very used, but it has very nice features. And the most important one, or one of the most important, is that it is, let's say, strongly dependent on age. So we can use the turn-on as a clock to precisely date a cluster, and it's independent of stellar rotation, because we are in very low mass stars, so rotation doesn't really affect these stars. So we can actually look for the main sequence turn-on, date the cluster, and understand if we have an age difference. And that's exactly what we did. So, sorry, another feature very important actually is that if you look at the main sequence turn-on here, in the CMD, it's not super easy to find, because like here are theoretical stellar models. In real life, you have uncertainty, so you have that this sequence is sort of spread. But what it does is that it translates into a peak in the luminosity function. So what you can do is just go to the luminosity function and see if you see a peak. If you see a peak, then good. You can try to match it with theoretical models. And so that's what we did. We got very deep HST observations of a young star cluster, which has the standing main sequence turn-off and the split main sequence, and the CMDs looks like this. So I think I don't have to convince you that there's a peak here. You can see that both here, and you can see in the luminosity function, and that is exactly the main sequence turn-on. So we can try to reproduce that with theoretical models. So we can simulate combination of different stellar population, and we can recover a proxy of the star formation history. Now, this is not exactly the star formation history, but is a proxy. And what you can see is that the azure, the blue histogram, which is the age distribution derived from the turn-on, is very peaked. So there is a clear peak, and it's very narrow. And especially compared to the turn-off age distribution, which is this very wide red thing. So the result is that basically we have no age differences in young Magellanic Clouds clusters. So from the turn-on, we can date the cluster, and we can say, okay, the maximum age difference that we have is like 4-point-something megayear, which is a very small. So it's not consistent with the residual age spread of a few tens of megayear or hundreds of megayear. So in 2022, we said, okay, rotation is still very important. Age doesn't really affect the CMDs of young star clusters. And then where do we stand? So since then, there has been a number of introductions to try and explain what is going on. So we can exclude this, and this is not random. This is the first to die. So we can exclude this. We know that this is like the most important feature, so stellar rotation. But then we have the role of binary stars. We cannot understand how binaries affect the CMDs, and we think that maybe they may play a role in the slowing down of the slow rotating sequence, but the observation actually do not support that model. Then we have merging. So if you have stellar merger, then you have a, depending on the merger that you have, you can have a different morphology, and you can reproduce the CMDs. And the latest introduction is circumstellar disks. So in one specific cluster, which is, so this one I just added, in one specific cluster, which is this sort of 2 gigayear cluster, we see this cloud of stars. And this is a near ultraviolet CMD. You see that these red stars are sort of very like heavily absorbed in the 275 filters. If we go to like redder filters, we see that this, like here in this intermediate CMD, they're still visible, But if we go to an optical near-infrared CMD, you see that these red stars now overlap perfectly the main sequence turn-off. So how can we explain this wavelength-dependent absorption? One way to do that is to include in the effect of dust. So if you assume that some of these stars have a like circumstellar disk, then their light is absorbed depending on the inclination of, between like the disk and the observer, then you have some this sort of spread. And basically these white points are stars with artificially added dust. So you see that here you have absorption that varies a lot. Here you have still a little bit, you have this bump here, but when you go to the near infrared, basically you have no distinction between normal stars and stars with circumstellar disk. So this could be actually a new explanation. We don't have so far observational evidence to support or like disprove this phenomenon, but it's there. So the situation is a bit of a mess, and we don't know what is going on. We know what is going on, but at the same time, we cannot explain what is going on. So for instance, even if you assume that you have a bimodal like distribution of the rotational velocity, then why do you have this bimodal? Is it like that at formation? Do stars slow down? Is it an evolutionary effect? Is it an environmental effect? We don't know exactly what is going on. And then again, so here is where we stand. And this is actually one of the latest developments. So this is the historic overview. The point is that I wouldn't say quite, but it's a bit complex. So it's not straightforward. Often people think that, okay, young star cluster is very easy. We understand them. Well, we do, but not to a very good detail, actually. So now, 2022, we have Gaia DR3, which, it revolutionized the field of open cluster. We can get better measurement in the astrometry, so better membership. We can get better photometry. But together with this, Gaia DR3 also published very good rotational velocities of millions of stars. So this is very important because in the context of the extended main sequence turn-off, it allows us to study not only stellar, like the photometry. So far, we just try to match the photometry with some models and to understand what is going on. What we can do with Gaia, we can actually directly investigate stellar rotation. So this is just a side note. So what does it mean to measure stellar rotation from stellar spectrum? So basically, the effect of rotation is that because of the Doppler effect, it causes a broadening of the line. So if you see a line and you have stellar rotation, then the line is broadened. If you don't have stellar rotation, the line is more narrow and more deeper. And on top of that, what you have is that you have a projected rotation. So that depends on the inclination between the rotation axis and the line of sight. And in particular, if you have an inclination 0, so you are observing a star like this, then you get no Doppler effect and you measure no rotational velocity. While if you look at the star like an inclination equal 90 degrees, so you look it perpendicularly to the rotation axis, you have a very wide broadening of the line. And what you can do is you can try to match the broadening with like a broadened spectra with your observed spectra, and you can recover this sort of the velocity that you have to input to broaden the spectrum. And that's exactly what Gaia DR3 provided. So we have a projected rotational velocity for more than 3 million sources. Now, the rotational velocity are actually good, but the RVS spectrograph was not designed to do the task. So they have, you can use them with some caveats, with some quality cuts, but you can see that from this line here, you have a fast rotating stars, lines are quite broad. If you go to a slow rotating stars, then you have lines that are narrower and deeper. So, okay, it works quite well. And the very good thing is that we have rotational velocity for for millions of stars, and many of these are actually in open cluster. So what we can do, we can use this rotational velocity to investigate a large sample of clusters, and not only from the photometry, but we can actually directly investigate stellar rotation to try and understand what is going on. So that's exactly what we did. So the first step was, of course, to select open clusters with extended main sequence turn-off, so younger than 2 giga year. You can see an example here. You can see that the turn-off is widespread, while the main sequence is very narrow, so very good photometry. And we can measure the spread exactly like we did before. And we can observe like how the spread changes with the age of the cluster. Then exactly like before, we can compare that with theoretical models. So this is like a mid-rotating stellar population. So you see that if you assume that the stars is rotating but not too fast, then you can produce a spread, but not as large as the one that you observe. If you increase the rotation rate, you get a better agreement. And if you go to almost critical rotation, then you have a sort of very good agreement. So these blue lines is the models computed for stars that are approaching the critical rotation rates, so very fast rotating stars. And what this is telling us is that, okay, fast rotating stars populate open clusters, and they can actually explain very well the spread that we have in color. But what we can do is we can actually compare the rotational velocities, and in particular the maximum rotational velocity measured in star clusters, that are the white dots, with the rotational velocity that we expect for population with different initial rotation rates. And you can see that, again, the blue line kind of overlaps very well with the points. We have this sort of plateau here, we have this drop, and then again this plateau. This point is a bit strange, but there are some explanation for that, so ask me about that later. And just 2 days ago, I basically redid this figure, including all the open clusters from the Hunter reference catalog in 2024. And you can see that if you put all the clusters together, you can still have a very nice agreement. So most of the clusters lies in this range here. So what this is telling us is that clusters, open clusters younger than 2 gigayear, are populated by very fast rotating stars. And this is very important and will be very important. So this is the first confirmation, both from photometry and from rotational velocities. So, okay, we have fast rotating stars. Is that all? Can we actually explain open cluster just by including a population of fast rotating stars? Well, let's try and see that. So what we want to understand is we want to basically connect the location in the turn-off, so the location here, with stellar rotation. And to do that, what we can do is basically verticalize this CMD. So we go from this sort of tilted distribution, which is a bit difficult to analyze, to something where this blue line corresponds to 0 here, this red line corresponds to 1 or 2 point something. But the basic idea is that stars that lies here will be on the left, stars that lie here will be on the right. And if we do that, and we compare that with stellar rotation, so with the rotational velocity of these stars, we can see that there is a very nice agreement, there is a very nice correlation between rotational velocity and position in the turn-off. So again, here we have the left side of the turn-off, and we have like slower rotating stars. Here we have the right side of the turn-off, and we have faster rotating stars. And so what this is telling us is that there is a clear correlation between rotational velocities of the stars and their location in the turn-off specifically. And if we put together all clusters, what we see is that they all sort of follow the same trend, in the sense that we have a very good correlation between rotational velocities and location in the turn-off. And if you look at this here, this is a bit clearer. So we have this sort of correlation. And yes, you can see that there is also like a color gradient, which means that like there is a correlation also with the age of the cluster. So as the cluster gets older, the maximum rotational velocity goes down and the spread in the turn-off increases. So you have this dependence on cluster age. And how can we explain this? I mean, can we try and see if the models predicts these sort of slow rotating stars on the left, fast rotating stars on the right? And if we look at theoretical isotones, we can actually reproduce this trend not by varying the rotational rate, but just by assuming a range of inclination. So what you see here is that this is a star observed pole-on, and pole-on means that the rotation that we get is 0 because we have inclination, like the Sinai is equal to 0. So here would be no rotating stars. Here we would be the maximum, the stars with the maximum measured projective rotation. So left side, V Sinai equal to 0, right side, V Sinai equal to something large. So qualitatively, just by assuming a range of inclination, you can actually explain the pattern there. And we can do something more. What we can do, we can try and completely simulate a CMD. So we can input a single or a combination of initial rotation rates. We input like a distribution for the inclination, so an isotropic distribution or something a bit more fine-tuned, and we can compare the CMDs that we simulate this here with the CMD that we observe, and you see again that you have these bluer colors here, red colors, so that's okay. And if we verticalize in the same way that we did for observations, and we compare again the rotational velocity and the position in the turn-off, you see that there is quite a good agreement between the white points, which are the simulation, and the orange points, which are the observation. So you have this sort of trend, which is not like linear, it's a sort of curved trend. You have a bit of scatter here, but the idea is that you can actually reproduce quite well both the CMD and the relation between the location in the turn-off and rotational velocity. And this is just done by assuming one population of fast rotating stars. So you have no need to include bimodal rotation rates, also because they would produce a spread here, which we do not observe. So we can exclude that, and we can just use a fast rotating population. And okay, so what we can do in open clusters by studying photometry and rotational velocity, we can actually reproduce observation with a population of initial fast rotators. Now, I want to stress that what we did is just assume an initial rotation rates, and then we let you evolve. So we can exclude that the bimodal rotation rate is, let's say, intrinsic at formation. We cannot exclude that some of these stars like slow down during their life. This is a bit more complex because, as I mentioned in the beginning, if a star slows down, then you have this, let's say, displacement in the turn-off, which depends on the peak, on the mixing, so it's a bit more complicated than that. But we can say that we can exclude a bimodal rotation rate at formation, and we can reproduce the spread and relation just by assuming that the inclination ranges from 0 to 90 degrees. So we can reproduce almost everything, but not everything, and in particular, we cannot reproduce the observed distribution of rotational velocity. So this is a bit tricky. We can reproduce it if we, let's say, design an ad hoc distribution of inclination. I don't know if that's really physical, and we avoided to do that in the work because I think it was a bit artificial in the sense that we don't have like the completeness of the rotational measurements in Gaia. We are missing a lot of things, so it would be, I think, artificial to try and mesh that. But on a separate note, this is not so unreasonable to assume that we have an ad hoc rotation, like inclination distribution, because if we look from, these are, I think, test rotational periods. So we have rotational period here, Gaia color here. The stars that we are considering are this one. So the hotter stars in the turn-off, and you can see that there is a bit of spread here, but there is no spreading period here. So this is sort of telling us that all hot stars share the same period. And for this particular cluster, which is 2548, we see that it has, in the turn-off, it has a sort of bimodal distribution of rotation rates. So this is rotation rate. We have a peak at low rotation and then a peak at higher rotation, which is this one. While in color, it doesn't show this bimodality. And what is very interesting is that from the analysis of test period and projective rotation, they detected that this cluster is consistent, or at least is okay, with a bimodal distribution of inclination. So it's not a given that all clusters have an isotropic distribution in inclination. They can have something more particular or something aligned. So this is 2024, and we see that in open cluster, we can sort of reproduce almost everything with a single population of initial fast rotators. Then this may slow down, may not, we still don't know that, but we can exclude the presence of a primordial bimodal rotation rate, which seems to be the case for Magellanic Cloud clusters. So now we have a new pieces to the puzzle. So the extended main sequence turnoff is common to both these objects, but there are some differences. And in particular, we don't see a split main sequence. And let's put the focus, we don't. We have some evidence of two clusters, two open clusters, but that's a different thing. So the next step would be to understand what is the origin of the bimodal rotation rate in Magellanic Cloud clusters. And we can use maybe, at some point, maybe we will have rotational period for stars in Magellanic Cloud clusters. I don't know, we don't have yet. We can use magnetic activity as a tracer for stellar rotation to understand if something is going on with like rotation rates and spin down. And the other things, as I was mentioned, circumstellar disk. So they may play a very important role. We still have to understand that. And I think that concludes the presentation because I think I'm running out of time. So there are some extra. So the last remark that I want to do is just, I hope I convince you that star cluster hosts very fast rotating stars and that the evolution of fast rotating stars is different from that of non-rotating stars. So what this means is that if we want to determine properties of star clusters, we need to include at least stellar rotation in the models. And in particular, if we want to get the age right of a clusters, of a young cluster in particular, we need to include stellar rotation. Otherwise, you see that the black line is the non-rotating isochron. The orange line is the rotating isochron with the same age. You see that there is a large displacement in the main sequence and in the turnoff. And in particular, usually we use the turnoff to the cluster. So it's very important if we want to get the ages right to use stellar rotations or include stellar rotation. So I hope you enjoyed the talk. Sorry, I was a bit fast, but if you, these are my favorite topics, let's say. So if you want to have a chat about this, please, I would be more than happy to talk. And yeah, that concludes the presentation.
So does anyone have any questions? So you reckon that there's not going to be any like initial bimodal distribution, but then you said like the magnetic clouds have, like we think they might have bimodal currently.
Yes.
What would you suggest is causing that difference in the spin downs?
So I think that the most reasonable assumption is to assume that like binary stars plays a role. So you have like tidal locking, so some of these stars slow down and they go and populate the blue main sequence. So let's see if I have it. The blue main sequence. This is reasonable to assume. However, observation at the moment do not support that scenario in the sense that we see similar binary fraction in the blue and red main sequence, which you would not expect if you assume that binaries are the cause of the slowdown. And there was one work for an open clusters. Let's see, sorry. Slide over. There was one work that tried to investigate exactly this phenomenon to try and detect binary stars among the slow rotating sequence. Where is it? Too many slides, sorry. Here. Okay, so they try to see, okay, if tidal locking is the cause for the non-rotating stars, then we should be able to detect some like binary stars, but I think they found only one. So it's like, at the same time, it's reasonable to assume that is the cause, but it's not supported by the observation. So I don't know. I would say that it's not a bimodal distribution rate at formation.
Yeah.
So all stars form approximately with the same rotational velocity, but yeah.
There's some hands up online.
Yeah, I was gonna say I think Chris was first.
So I had so it seems to me entirely unsurprising that the inclination angles of the stars to our line of sight would not necessarily have an isotropic distribution. I mean, it's basically a reflection of the net angular momentum of the cluster in which the stars form, and that tends to be correlated between stars within a cluster. So I would expect that you may have them all pointing in one direction or vaguely in one direction, or possibly vaguely in two directions rather than being uniformly distributed. The other question I had was, you showed right back at the start the wonderful globular cluster color magnitude diagrams from Jay Anderson and co.'s work. And those all get cleaned up by doing proper motions on them in order to get rid of background objects. Has that been tried with your HST observations in the Magellanic Clouds to clean up those color magnitude diagrams?
Yes, so very good point. So to answer, not to answer, but to reply to the first comment, I agree with you. So there is a correlation between like the angular momentum of the cluster and the inclination, and this like inclination between the stellar rotation axis and the line of sight, which is not super easy. I mean, it's easy to understand, but it's not super easy to measure because there's a lot of uncertainties. And when they try and do that, when they tried to do that, they detected that most of the clusters are actually consistent with an isotropic isotropic distribution of inclination. So I think it could be like a selection effect or something like that, but it's easy to understand, I think, not so easy to prove. And concerning the second point, yes, so all these, I mean, I'm not sure about these two that I plot here, but we usually do a two-process decontamination. So if we have proper motion, then we use those to select only cluster stars. And like for the CMDs that I showed later with the highly absorbed stars, that's exactly what you did. And the other thing that we can do is to try and see how does the photometry of the field look like, so that we can sort of understand what is the level of contamination that we have. And we do both. So let's say that we can safely assume that the CMDs of Magellanic Clouds cluster that we have are only populated by cluster stars. So we have no contamination from field stars. So we do both, like a proper motion cleaning and the CMD cleaning.
Okay.
Caro.
Yeah, I might have missed it, but so at first you spoke about both the globular clusters and the open clusters, and I wondered how this result of the rotation applies, or whether it does apply to globular clusters, which are kind of a different beast. They formed a long time ago in a universe that was very different to the one we know now, where the open clusters are forming. So that was my first question, I suppose. And the fact that most globular clusters, as far as I understand, show minimal rotation, so they would be more consistent with a isotropic. Perhaps, I don't know if you've looked at that, at the rotation projection for those. Yeah, so I guess that's kind of my two questions. How this applies to globular clusters. Oh yeah, and I had another thought as well. Do you think something like Omega Sen actually has real age disparities, and whether, like, you know, if rotation also is sufficient to explain that one? Thank you. Great talk, by the way.
Thank you. So all of the questions are very good question, very good point, and very tricky one as well. So to answer the first one, we think they're actually different objects now. So we know that like open clusters and globular clusters, like completely different in terms of like properties and formation environment. And so I wouldn't know how rotation actually affects these globular clusters. So we know that like stars spin down. So by the time to get to the age of globular clusters, they're basically very slowly rotating. So they're not affecting the cluster anymore. If it affected the clusters originally, then it's a bit more difficult to say, but there is some scenario that assume that stellar rotation and fast rotating stars are actually the cause of the multipopulation in globular clusters. So there might be a connection with stellar rotation. It's quite difficult to say. What I can say is that, yes, open clusters, like the evolution of an open cluster and a globular cluster is completely, they're completely different. And what was, sorry, the second point again?
Yeah, I was wondering about Omega Sen, and if you thought that was yet another different class where possibly age differences might be real in there.
Okay, so Omega Sen is, I think, There are many theories about that. The most common one is that is like the remnant, the strip nuclei of dwarf galaxy. So I would say that it's not your prototypical globular clusters. So it might have age differences that I think it depends on how you classify like an age difference. So if you have to assume that you have multiple star formation episodes to explain like the trend with metallicity or the trend with light element abundance, then I would say yes. That's my like opinion. So I would say that yes, it can undergone multiple star formation episode, and you have like the enrichment in metallicity, you have the enrichment in light element abundance, so you have like multiple sterile generation of stars. Then again, it's not, I don't think you can apply straightforwardly to all globular clusters, but we think that there is a whole class of globular clusters that is exactly like omega sen, like so the strip nuclei of dwarf galaxy, because we see some heavy element variation in this cluster. So yes, it might have some age differences, but I would say that this is not related to what we see in like young star clusters. So totally different beast, as you said. Yeah.
Thank you.
Any last questions in the room?
I will monopolize you later.
Yeah, it's nearly 2 o'clock now, so thank you for the talk.
Thank you.
And we can thank them again. And you're going to be around for the rest of the day and tomorrow, right?
Yes.
Yes. So if you have any questions, ask them then. Okay. Be in the postdoc office.
Thank you.
Thank you.